In this video, I'll go over the different types of steels with a focus on welding. In this video, I'll make use of 2 tables worth of all kinds of steel samples, as well as the laptop and the smartboard over there. Some of the footage will be handheld, some of them will be shot off the tripod there. In this video, I'll be focusing on steel classification terminology. Some of these terms, about 12 to 20 of them, depending on how you want to count them. Some of these terms would include carbon steels, mild steel, high carbon steel, Austenitic steel, high-speed steel, spring steel, and especially focusing on how all of these terms relate to steel classification, how these terms relate, and how steel nomenclature or naming of steels are structured. So let me just focus this camera here. There, that's about good there. And we'll start at the whiteboard here with a couple of memory joggers. The first one is a couple of definitions. Oh, actually, I'm going to have 2 visual approaches here. This one that's covered by a screen that I can pull down is going to reveal a tree-like structure, but it's not like a tree, it's a menu tree such as you would find in a cell phone. Another visual that helps with this is this potato shape here is going to be groups. It's going to be groups of steel and subgroups in different subgroups and more subgroups in smaller subgroups. So it's going to look like this. So this is going to be a bunch of groups or potatoes, and the other one is going to be a straight up and down menu tree. So visually different, same content, exactly the same words on both of them. Before we go anywhere, a little memory jogger here, that steels are, and this discussion is coming out of this previous slide here, where different phases of matter were discussed, how they are named, some terminology. So steel is an alloy, and alloys on the bottom of the page here are solids mixed with solids. So that's what those kind of physical mixtures are alloys. And very important for welding, these physical mixtures, all of them listed there on the board, they separate. They are physical mixtures, they are not in chemical bonds. Okay? And how do you mix solid with solids? Yeah, you have to melt them down, the 2 phases of solids, and then stir it up, and as they freeze or solidify, whatever temperature that may be, as those molten solids solidify, then it makes an alloy with a nice even distribution of the 2 alloying or 3 alloying elements, or 4, 5, 10, depending on what you're cooking, because it's very much like cooking, making alloys and metallurgy. The number of ingredients you have, you want them evenly distributed in an alloy. You don't want them clumping in one corner, all the spices and all the meat uncooked in another corner or some such thing. So at the steel mill, the manufacturer makes sure that the product comes out is evenly distributed elements in a soup of molten steel. So that's where this definition for steel comes from, right over here, that it's an alloy, a physical mix of 2 solids or more, an alloy of iron and carbon, as well as for seasoning there's a little bit of manganese in it. That manganese is usually about 1%. We'll go with that number, it's an easy number. Technically it's between 0.3% to 1.65%, just go with 1%, okay, that's an easy number. And the carbon content here is topping out at 2.1. Now between 0 and 2.1 there's a whole lot of numbers, and the numbers of course continue beyond, on a number line, beyond 2.1 they are called cast irons. Not discussing cast irons, so all the steels end at 2.1. With that said, and that definition there said, we're good to go for our first groups. Oh, one more thing, I'm going to be using the symbols of the elements from the periodic table of elements. So up here in the corner, C stands for carbon. Throughout my notes that I'm going to write, C will be consistently carbon. And carbon is not a metal. The rest of the metals are here. Titanium. Let me just turn the camera just a touch. There, titanium in the corner, vanadium, chromium, manganese, iron, cobalt, nickel, and further down there in the middle is there, molybdenum and tungsten. W for tungsten. And one more note here, that carbon has many forms of carbon depending on its crystalline structure. It could be graphite, so that's what's written here, graphite, coal, or diamond. Those are all forms of carbon. So, what relates to welding, of course, is going to be the word graphite most often, although for grinding and cutting diamond saw blades and diamond grits impregnated in and made into abrasive product is also related to welding. So that stuff, these words here, is not going away anywhere. Let's get going with these steel groups. In this big bag of groups, and I want to explain just one more thing. How is this math? There's going to be percentages, okay? That's one thing. And two, these groups, there is a math word for these groups. This is sets, okay? This is one set. This is the set of steels. In this set, there will be subsets. And within those subsets, there will be other subsets. So how is a student going to be tested on all of this terminology and all of this body of knowledge? One, you'll be identifying steels, and two, there's going to be true or false questions related to steels, such as all steels are alloys, true or false, or all alloys are steels, or some, I'm just inventing these sentences a little bit, some high-speed steels are tool steels, all tool steels are carbon steels, none of the carbon steels are austenitic. So those kind of items that you have to think through, that will test you if you really have an understanding of the meaning of the steel terminology for classification of steels. Alright, let's get going with these groups, and I color coded them. The first group is going to be a red group, and it's going to correspond to a red list of items in this view that I'm going to reveal slowly as we go along. The next group will be a group of green, a group of black, and a group of blue. So we're going to go counterclockwise, I guess. Wherever you're watching, it may be called anti-clockwise. So the first batch of words, it goes into the red group, and that group is called carbon steels. So I'm just going to write carbon. There, so that little C just means carbon steels. So the name of this first group is carbon steels. In this group there are four little subsets. The first one is low carbon steels. The second's name is mild steel, medium carbon steel, and high carbon steels. So those are the first four subsets within the group carbon steels. Why are they carbon steels? We'll stop right here. Why are they carbon steels when we just reviewed the definition of steel, that all steels contain carbon? I don't know why these are carbon steels, that's the answer. However, the group is just named carbon steels. So these steels contain carbon, these steels will contain carbon, these steels will also contain carbon, and these ones will contain carbon. But this group or subset is just named carbon steels. Alright? It's been named so in the 1880s or so. And this is the terminology that follows the Society of Automotive Engineering or American Iron and Steel Institute terminology. But yeah, so on the other slide here we've got the same first four here with some numbers to it. So see, group 1 is carbon steels, so 1.1 would be low carbon, 1.2 is mild, 1.3. So these numbers again are not the steel numbering system, they are just showing you how the terms high carbon steel, mild steel and the rest relate to the rest of the terms that's coming up. The carbon content in these groups is notable or noteworthy. That's 0.05%. That's not 5%, that's not 0.5%, that's 0.5%, okay? That's how much this carbon is. 0.5%. Sorry, 0.1%, my bad. Alright. And you can see the numbers, I made them easy. No, I didn't make them easy. These numbers are fairly easy. These numbers are from the SAE numbers, standard situation here. Weldability of these steels. Let's go over to the steel samples and let's see what you can do with these samples and how they look like and what's being manufactured out of them. So for identifying steel, you have a couple of options. You can have a spark test done on a grinder, but that's not bad, but it's a little Stone Age. It's not because it's an old way of testing method, but it's I mean that it doesn't tell you much. Much more information is coming out of what's being manufactured out of the steel. Okay, so first group here, low carbon steel. So this is why it's laid out this way, carbon steels. So these guys, 1, 2, 3, first four groups, these are all carbon steels. So what's being made out of steels is way more telling than any spark test. The softest steels are low carbon steel. We'll start with this nail. This is a classic example. If you drive a nail such as this halfway into a wood like so, you know you can bend it with a hammer repeatedly, left, right, maybe a dozen times. I have a separate video on this, and depending on the nail's diameter or size, it fails sooner or later, but it takes about a dozen or more bending over or bending the nail before it snaps. So this kind of steel is very soft. Okay, I'm trying not to use words such as ductile, malleable and other technical terms which have precise meaning, so I'm just going to go with the generic words soft. This is a soft nail product, and they rust. All of these steels rust, with the exception of stainless steels coming up later, and all of these steels could look rusty like this, or could look highly polished. They can be coated, they can be painted, so color is not helping. They weigh the same, they are tasteless. Don't be licking any of this. Some of them are galvanized and they are toxic, but I'm just saying they are tasteless, odorless and whatever. So color doesn't help a lot. It's in identifying steel, it's about 80% of the information that's coming out of what's being made of the steel. So we have, of course, rebar. So because the nail bends easily and is this one bare, and it rusts quite readily within 15 minutes if you leave a bag of nails out in the rain. You can see a similar product here, some cotter pin that's used in automotive applications that goes through a hole at the end of an axle that keeps a nut from spinning off at the end of an axle. Here just happens to be such an axle with its thread on it. Let me just adjust the camera slightly, there. And you get the idea. The nut is not here with me, but this is where the cotter pin is going through. Okay, these are readily weldable, and you can see this one is a sheet metal ductwork here. You can see this line here. So the overhead ducts for air conditioning, heating, ventilation, whatever. You can work it with a pair of tin snips very easily. manufactured product. Here is one example. This is a duplex outlet for the electricians there, something like that. So that's behind the faceplate. There is this box, and this is where you can do your wiring connections. You can see that there is circular holes punched through it. This is how it's manufactured. It's made by punching, or it's made by punching, so the shapes are crimped. You can see that there is such crimping over here. There you can see metal folded over onto itself to join the sides of the box. So the point of this type of soft metal is that when you make bends with it, they don't break. They don't crack out here where the bend is the strongest. So you can repeatedly bend them over, same as with a piece of tie wire. That's why I have this one with a little piece of tie wire left on it. Okay, so whether it's sheet products or wire products, these are also wire, just thicker. They are very soft and they are readily weldable with no precautions, no concerns, no nothing. I also have here a piece of tape measure. Of course, you can tie a knot on it, maybe not with one hand, but you get the idea. A very soft form of steel. The next group is mild steels. They are stronger than these ones as they have more carbon in them. Not a whole lot more carbon. If we go back to the table here, how much more carbon? There, those are the numbers that we had. So we are here mild carbon. So a little more than 1/10%, 2/10%, or 3/10% carbon, and that difference, it makes a lot of difference. So these products here are still weldable, and they are actually made by welding. As you can see, this weld in this pipe in the middle of that one, or this hollow structural steel shapes, such as this one. You can see this pooling here is how this has been welded at the factory. Some other examples include welded chain. Of course, it's named welded purposefully. You can see some similarity to nails and cotter pins. You can see that this bend here has a quite sharp radius, and you do not want the chain links to crack out here on this side. And once the chain link is bent together, it's welded here in the middle. Alright, there are different grades of this welded chain. So some of the chains don't use mild steel, some of the chains use alloy steel. Don't worry about it for now. We'll go with an example of mild steel. Okay, and so it's welded. The same principle applies to this item here that's used in its name is a shackle. It's used for hoisting and rigging and lifting heavy things with chains and wire ropes and such. So again, the same idea applies. It shouldn't break and crack here on this side. And in use, it's very important, when this is in use, it should plastically deform somewhat. It should have a lot of give, like maybe not so much there, you know what I mean. It should have a lot of give and a lot of flexing and bending before this product fails. The point of this product being made out of mild steel or I-beams and these kind of things, that they bend and flex and deform visibly a lot before failing. Instead of snapping suddenly without any warning, they should be, for safety reason, these should be able to visibly deform, so they can be seen that they obviously underwent some overloading. Okay, to make this overloading visible, these have to be made out of mild steel. Same applies to chain. If these links, they have a lot of stretch to them. If these links are visibly deformed and elongated, you know that the chain has been overloaded. So that's why they make them out of mild steel. What do we have here? A product a plumber uses underneath the sink. Again, similar idea. You can tie a knot on this thing and it still doesn't break. can't tie a knot with one hand. No, I haven't practiced before the video, but you get the idea. Mild steel and a motorcycle chain. You can see the similarity between the chain links here. These plates on a motorcycle chain need to be stamped out of the metal, just like the stamped out or punched out holes in this plumbing product here is made. So similarly, this motorcycle chain, the links here, whether it's the golden colored one or the other shiny ones, whatever, inner plates or outer plates are all mild steel, and of course the chain will work with a sprocket there, and it's gonna be spinning on an axle or a shaft. So last mild steel item is a saw blade, but this is not a saw blade for a power saw. This is a hand saw blade. This is also very easy to bend, you can see, and it's got a lot of flex to it. Just like the rebar had a lot of flex, it's supposed to stay in the building, to sway with the building and not fall apart, not crack and snap suddenly and everything catastrophically collapses. So likewise, this saw blade also has a lot of flex like that. But if anything is soft, it of course is not going to cut successfully, so the teeth are hardened on this one, but that's another story. So mild steel or so. So these two groups, mild steel and low carbon steels, are readily weldable, grindable. You can slice and dice them easily. The other two groups, not so much. These are only weldable with precaution and preheating and post-heating, and that's why we have here 2 jars of honey. Gonna explain it in a sec. So just quickly, the samples here that we have: wire rope, threaded connections, threaded connectors, either bolts or this one is part of a vise, and we've got this motorcycle axle here and the sprocket below. So motorcycle axle is not like a rebar that you can bend. If two of us, two students would get on it, they could probably easily straighten that one. Oh, the reason why it's green is it's got an epoxy coating so it doesn't rust. That's all there is to it. And this motorcycle axle, if 2 people get on it, it's not going to be bent back into straight anytime, or bent anytime soon. So all of these threaded connectors, the threads need to be holding their shapes. Okay, the threads, we know the threads can be stripped out, but the threads also need to hold their shape pretty consistently, and somewhat of the same applies to wire ropes. Now of course this one, as it is, has a lot of give, and really I don't really have to press it hard, but the reason for the amazing flexibility in this is due to its braiding and construction. The steel itself is medium carbon steel. Some of them are made out of high carbon steel, but we'll go with medium carbon steel on this one. And flexible snap rings could also be made out of medium carbon steel, especially the cheap ones. High carbon steels are files, some drill bits, especially the drill bits that can be sharpened by those files along their cutting edges. So these kind of drill bits, hammers and pliers and chisels and razor blades and X-Acto blades, some plain blades, screwdriver tip, and of course we've got here a very noisy bearing from an elevator. So bearing balls, outer race and the inner race are high carbon steels. Now of course quality bearings can also be made out of alloy steels, or same for chisels and everything, but the cheap ones and the simple ones, or most of them, can be made out of high carbon steel. This group is not really readily weldable. Think about it. Can you drill a hole into a chisel just so you can hang it on a nail? No. It's not happening. If you tried it, it's not going to work, because the drill bits are not significantly harder than high carbon steels. So these are very hard steels. You're you're pounding nails with a hammer such as this, and the face of the hammer does not deform. The nails deform, the nails bend repeatedly, but the hammer doesn't change its shape. So you cannot successfully weld hardened items such as these. This one here is a tap and die. This is a tap, and I drilled into a bolt that broke at one point. You can see the drilling was a little bit off-centered, and it was miserably hard to drill into a medium carbon bolt, and the high carbon tap couldn't really be successfully welded to a medium carbon bolt, and yeah, it's a misery. These items are not really weldable. They are not designed to be weldable or fixed together by welding, and the reason for it is gonna be explained by this honey, and the term is precipitation hardening. What happens to the high carbon content in high carbon steel and medium carbon steel is that the carbon content will precipitate out from the solid solution as graphite. So let's look at this honey a little bit. So honey is normally liquid. In the liquid you have sugar green, granular sugar. So in liquid honey you have solids dissolved. Okay, liquid into solids, that means that this is a suspension. Okay, not as a car suspension, not that suspension, just as two physical mixes together. This is a suspension. So the sugar grains are suspended and dissolved temporarily in the liquid honey. What you can see over here, this white spot, is that the sugar, of course, crystallizes out of the honey. It precipitates out of the honey, starting anywhere. It doesn't necessarily have to settle on the bottom. It can start anywhere along the side, and this is how, of course, the finished precipitation looks like from an oversaturated solution that contains more dissolved sugar than it could actually hold in a stable manner at room temperatures. You see that the sugar just crystallizes out. So exactly the same is going to happen to high carbon steels and medium carbon steels. As soon as the welding torch hits them, the solids that are dissolved in the alloy, they will start, the carbon will start trickling together into little streams and little rivers and whatever, and will form flakes, and those flakes will run to the high heat, and it's gonna precipitate out of the original even distribution is going to be changing like this. It's going to be lumps and clumps of graphite flakes, along which the product will fail. Okay, because graphite doesn't hold. Graphite is what you have in a pencil, and pencil is meant to be the graphite layers flake off and shear off and leave a nice and even layer on the paper. So that's exactly what happens. If you try to weld back a claw on a broken hammer, it's gonna fail repeatedly along the original break line where graphite will be separating out. You can see it black, you can see it as soot or some, so there's going to be the graphite layer along which this will fail repeatedly if you try to weld back these kind of things. These ones are not so bad. So you know, if you weld a pliers back, it's gonna hold, but not for long. It's gonna stick together, but just barely. Okay, it's not gonna really work. Same for a bolt. If you try to weld a bolt back together, it's not gonna have nearly the same strength as the original. All of these were made by forging, whereas these can be made out of punching, like with a cookie cutter, out of a sheet of dough, out of a sheet of steel. You can punch these things easily. These ones are made with forging, and they can only be machined. So, and that doesn't mean drilling. So that's what happens with these products. Let's go over to the second. The name of the next group is gonna be in that green potato there. That set will contain alloy steels. I kind of pre-printed it, and we'll stop here again. This alloy steels is just again the name of this group. All steels are alloys. These are alloys, these are alloys, these are alloys, and these are alloys, but the name of this group is just alloy steels. I know it's confusing, but I didn't invent this terminology. I'm just telling you as it is. So I pre-printed them so we can go a little faster here. There's a lot of detail, but none of this stuff is gonna be featured in the quiz. So there are manganese steels, nickel chromium steels, molybdenum steels, chrome molybdenum steels, nickel chrome, sorry, there's one letter missing there, nickel chrome molybdenum steels. There are nickel molybdenum steels. What do we have here? Chromium, chrome vanadium, tungsten chromium, and silicon manganese groups in the group of alloy steels. So I should have pointed out maybe that silicon also lives right here next to carbon or underneath, so these elements are relatively close to each other. So none of these groups in the alloy steel group is weldable. So that's basically end of the story, but I have just two samples to show you with this one. They are here. The wrench is here. It says chrome vanadium steel on it. So that means that this belongs to the alloy steel groups, and this one is also chrome vanadium. Yeah, chrome vanadium, and it says drop forged. So you can, if there isn't a hole in it already, you can't make another hole in it. They make gears and gear teeth out of alloy steels and metal that's case hardened, such as the journals, the bearing journals on a crankshaft. Often these products are hardened in special manufacturing steps so that the outside of these surfaces is hard and the inside has a little give so it withstand the forces that's placed on it in normal operation inside the engine. Massive amount of shock loading from the combustion process that's cyclic in its nature, so it's not evenly loaded. It's bam, it's loaded at one point and then not for a little while, and then bam again loaded, and so because of its cyclic or cyclic loading, it's a composite product. I have here other smaller gears here. Okay, none of this stuff. If the gear teeth break off, good luck welding it back. It's not really going to be successful, much like for the same reasons as they are either based out of high carbon steels, or they are based out of medium carbon steels typically, and on top of it, like I said, they have this sandwiched structure to it, a harder case hardened, and a softer inside. So as soon as the welding torch touches it, it's gonna change the hardening, this layering in it. It's not going to work. All right, end of that story. So they are not hardened, or not really weldable. Next group over here will be stainless steels. Let me just switch the light off. Stainless steels are fairly straightforward. They have just, I'm just going to go with 3 words. So this is the group of stainless. Some stainless steels are weldable, some others are not. Again, based on carbon content and other stuff. Okay. Actually, most are low carbon steel. Some of them are high carbon, so they are not weldable. Such as a chef's knife is not high carbon, based on high carbon content, or has high carbon content and is not weldable. Some other stuff like automotive muffler systems, they are highly weldable. So most of the stainless steels are weldable. Some words that I'm going to write up here. Austenitic. It's a person's name. It was a British metallurgist or engineer or some such person Mr. Lord Austin. So another one is Martensitic, named after some German guy, Herr Martens, something like that. And just one more word, duplex. Duplex meaning steels that have some of the features of these and some of the features of those. Okay, that would be fairly straightforward. But there are also super duplex, there are also ferritic, and so there are different stainless steels. But that just to give you an idea, just to get started. And let me show you here the visuals that we have here. Is fairly straightforward. Besides the sink over there, which is also made of stainless steel in its entirety, then the stainless steel is, some of the stainless steels are highly formable, so you can make sharp corners and sharp bends without breaking out. Okay. Some other items that I have here have been submerged for more than a decade, and they are not showing corrosion. They are stainless to the degree that they are rust free. Okay, such as this one and this one. So these are samples of Austenitic stainless steel, the first group that I have there, and they are not magnetic. This is a magnet, and like there, that's magnetic there. This steel is not magnetic at all. What I have here is this little scissors, not magnetic up to that point. Beyond that, starting with the little screw, no, it's actually a rivet, and the blades, you can see the blades have different color than the handle, and the handle also is maybe chrome plated on top of it, whereas the cutting blades are bare. The cutting blades are magnetic, you see. So this kind of stuff is Martensitic stainless steel. Chef's knives that you can keep on a magnetic strip on the kitchen wall where it should be dried instead of thrown into a drawer. And of course I have tweezers and dentistry tools. So all of this is magnetic. They also rust. Not right away. They are stainless, so they stain less than usual, but they are strongly magnetic, all of them, there with a loud clunk. And you can see some of this rusting there on dental explorers, and that's an explorer. This is for removing scales from the the calcium deposit from the teeth. And this tweezers is also rusty somewhere. There you can see at the tip there we have just enough good light for that, so there it's rusting, and the dentist throws it away after a while. And that's the end of the story on these Martensitic stainless steels. So these ones are not weldable. Don't even try, it's not going to happen. They have high carbon content, so they can be sharpened. Coming back to the tools here, high carbon steels that hold a sharp edge. Sharp edge, sharp edge. Edge is not so important on a hammer, but there are small edges on the pliers over here for wire cutting. Let's see if I can. There, so you get the idea. There, those beveled surfaces there in the middle for wire cutting. Okay, and of course the jaws on the pliers also shouldn't deform. They do eventually, or especially on bolt heads that aren't too much softer than the pliers jaws. But so sharp stuff, high carbon content. Sharp stuff, high carbon content. High carbon content, unweldable because of the graphite precipitating out. Same story repeating here, alright? So don't even try. This kind of stuff, highly weldable with the appropriate electrode or filler metal and everything else. So that's all about stainless steels. The next group is coming up over here. And let me just switch off the light. And we can also look at this layout here. Sorry, I forgot to include this one. So there's the alloy steels. That's how that looks like. The alloy steels, I didn't write them all of them up. Sorry, I was lazy. It also doesn't fit the page, so it's a little bit both. Or like it doesn't fit the page, we'll go with that, because I have a page on which on which this menu tree does fit, you see, and it kind of doesn't fit the page. So out of the 10 or so groups, I just listed the first 4, and the numbers that go with the alloy steels is 1 to 5% alloying element. One more thing there, manganese is about 1% there, like I said, and we have a group here, manganese steels, with you can see more than 1% would be the number that goes with it. In reality, it's about 2 or 3%, whatever. Just, you know, for all of the steels, it would be under 1.65. For manganese steels, it's over 1.65. Whatever, just close enough. Just that would be the idea, that it's got a higher percentage of the alloying element, whether it's chromium, vanadium, molybdenum, nickel, tungsten, whatever it is. So that's that version. And the stainless steels of course look like this. There. The stainless steels are stainless by definition because they have at least 10.5% chromium content. Some sources say 11, or some sources say 10, whatever, just go with it, it's close enough. You're not going to be licking it or testing it for chromium content, and these for actual quantity. So for our purposes here, this is how the terms relate. So these are subgroups or subsets of the set or group stainless steels. Very straightforward. The next group over here is gonna be the last group, the last major group, sorry, and this one here. And its name is tool steels. Tool steels, and we're gonna stop right here again. Tool steels, we've just, and I don't want to walk over there again, we've just seen hammers and other tools and chisels and plane blades made out of high carbon steel. So why is this called tool steels? Again, I don't know. I really don't. I have my good guesses, and it's going to be a little obvious, but it's just called tool steel. So if you have wrenches, you saw the chrome vanadium wrench on the table, you know, don't get confused with what's being made of the steel and how it's actually named, okay? So that's tool steels, that's the name of the group. Inside the group there are 4 major groups, and 2 of them will have little subgroups. So we have high speed tools. Don't confuse it with high carbon steel. High speed steel, high carbon steel, completely different animals, okay? The next group is cold working. Cold working. And the next one I want to write up is water hardening. Water hardening, and the last one is shock resisting. Now there are other groups as well. There is also hot working as well as cold working and other groups. Don't worry about it, this will get you the idea. Especially that these tool steels, the first 2 groups, not the first 2 groups, sorry. The first group, the high-speed tools, are designed and made to work at rotating workpieces such as on a lathe, whether it's woodworking or metalworking. High-speed tools or high-speed steels, as they heat up, working on a high-speed rotating workpiece, as they heat up, they do not soften, they do not dull, and they do not lose their edges. None of this stuff is weldable, so completely forget about it. These tools cannot be successfully fixed because they are special alloys, and because of its carbon content as well. Okay, again, in welding they might stick together barely or temporarily, but it's not going to be holding with any amount of strength. High-speed steels are of 2 kinds. Some of them are tungsten based, and I'm going to go W on it because that's you're going to use the symbols consistently from the periodic table of elements, and the other one is so tungsten based and molybdenum based. That's MO, molybdenum based there. Okay, so those are the two subgroups. And in cold working steels we've got two subgroups. One is air hardening and oil hardening. There, I know that it's microscopic writing and it's hard to read, so that's the names of the steels. Cold working tools, of course, have a purpose that they can only be part of hand tools where they are not subject to high heat. The terms air hardening, oil hardening and water hardening relate to how the tool was made. At one point it was quenched on air, at whatever temperature air, in oil, whatever temperature oil, it's detail later, and in water. Shock resisting tools, I think that's a good name. They resist impact, and impact that's associated with power tool use. Over here on this kind of layout we've got the last slide here, or the last part of the slide. Actually I'm going to get rid of it entirely. There, the tool steels, that's how they relate. So these are molybdenum based and tungsten based are subgroups within the high speed steels, so you get this. That's how these terms are structured. And over here, let's just get the light on. Over here at the table what I have is this one is an M2 molybdenum turning tool manufactured by Henry Taylor Tools in England, Sheffield, and so they belong to the tool steel groups like so, high speed steel. So this is molybdenum steel, it's M2 actually. This drill bit is unknown, but it's high speed steel drill bit. I don't know where this came from, and the whole set, or whether it's tungsten based or molybdenum based, I don't know. This same case applies to this Ryobi surface planar blade. All it says on its backside here is that it's high-speed steel. Okay? If you go to the store and you look at high-speed drill bits and high-carbon drill bits, the high-carbon drill bits are dulling a lot faster than high-speed drill bits, because in the heat of work, whatever heat is generated, whether it's drilling into wood, copper, aluminum or steel, mild steel is being drilled, yeah, then these still dull fairly fast, whereas high-speed steels don't. Okay, so that would be the idea of paying more for high-speed steels. You can get economy drill bits, the El Cheapo kind, made out of high carbon as well. And if you're using power drill, if you're using a brace or a hand drill, these will work fantastically well for a long time. Okay, so these are more for like a drill press. Air hardening and oil hardening steels, I just have two of these plain blades for show and tell, and that's it. They're not weldable, leave them alone. Last two items to mention, and I know it's a long video, thank you very much for watching so far. Last two items on this chart will be spring steels and HSLA. They live somewhere between the alloy and the carbon steels. Spring steels are not new to science. Let me just change color here on, how about this kind of purple. So I'm gonna write spring steel, just like spring steels here. Some of the spring steels are based out of high carbon content, some of them are based out of alloy, and some of the springs are of course stainless steel springs. So, and again, some of the springs are copper springs. So you can make springs out of a variety of materials, alright? So that's why that word is kind of floating among those three sets that are already in place. Last word is, I'm just going to abbreviate it like so, high strength low alloy steel. High strength low alloy steel is used basically or most often in automotive products, making structural strong automotive bodies, so they can make the car bodies thinner for fuel economy, so less mass you carry, the more gas you save, but basically less mass you accelerate, the less fuel it consumes, and some of the structural steel, the I-beams or channel steel, Ls, pipes, what have you, hollow structural steels, they can also be made out of high strength low alloy. Again, higher strength than the structural steel or mild steel, but the same size, so the components wouldn't be thicker and bigger. How this looks on the other version here is they are at the bottom of the list like so. There, high strength low alloy, and the spring steels with the applications that I mentioned, they are listed there, so they can be based out of those. The last one is Cu based, so that's copper. And what I have here on the table here is, of course, some auto body components. You can see these are highly weldable, grindable. This is fender and body panel, and this is, you can see that these flanged nuts here were welded at one point by the manufacturer to these locations before it got coated over with this gray coating, and it's been produced by spot welding. Some of the spots here in spot welding, not that one, but that one, and that one I had to grind off. It was a little sharp to my liking. So highly weldable, very soft form of steel because it's based out of mild steel. Spring steels, yeah, don't mess with them. They have too much carbon. If they break, tragic, get a new one. So they're not weldable. Yeah, end of story about springs. This one is compression spring. You can see the coils will get closer. This one is a coil that's for extending. It's an extension spring from a sofa or something, had a hook failure on it. And this one's from an elevator shaft. It's from an elevator. Alright, so that's basically what I wanted to share about the weldability of these things. So these ones are highly weldable, as well as these ones over here and these ones. So the rest of them, with caution or none at all. These are highly weldable or none at all, and completely forget about these ones for welding purposes. So that would be the lay of the land. Thank you very much for watching. Have fun welding and metalworking.